If yes, then.
Yes.
Okay, thank you very much. So, thanks everyone. Welcome for joining this joint FAO and Global Network webinar today. My name is Alexander Loschke, and I work at the UN Statistics Division, UNSD in New York, in the Data Innovation and Capacity branch. I'm extremely happy for this opportunity to co-host this webinar together with my colleagues from the Food and Agriculture Organization, FAO, of the United Nations in Rome. UNSD and its global network have a fruitful history of cooperation with FAO in organizing webinars on a variety of statistical topics, and you will see other webinars coming up in cooperation with FAO in the coming weeks and months. For example, on SDG indicators, classification, and the use of artificial intelligence, to name a few. Our joint FAO and Global Network webinar today will provide you with an overview on the use of Earth observation data for agricultural statistics. Our speakers today are Pietro Gennari, Chief Statistician of FAO, and Lorenzo de Simone, Geospatial Technical Advisor at FAO. They will present on the EOSTAT project and will highlight FAO's work in building countries' capacity on the use of Earth observation data for the production of agricultural statistics. They will give some highlights, high-level insights on the main innovations introduced in the field of Earth observation-based crop statistics, which were implemented by FAO through R&D and testing in countries in collaboration with academia. They will also talk about how the innovations brought by EOSTAT offer a solution to overcome the challenges connected with the collection and predication of crop statistics, using both traditional field survey-based methods and the EO-based methods. This webinar is the first in a series on this topic organized by FAO during the months of March to May. And Pietro and Lorenzo will say more about this later on. Before I hand over now to Pietro, just quickly some practical things. So we will first hear the presentations before we will have a Q&A session at the end. During the presentation, feel free to write comments and questions into the meeting chat at any time. During the Q&A session, you will be able to ask for the floor by raising your hand, and then you can ask your question yourself if you wish. As always, this joint FAO and Global Network webinar is being recorded and will be made available on the global network of data officers and statisticians at yammer.com/UNstats and on the FAO event website for this webinar. So now over to you, Pietro. The floor is yours. Thank you.
Thank you, Alex, and good morning, good afternoon to everybody, and thank you for joining this webinar. So I will provide first a brief overview of the project that we call EOSTAT project, so statistics produced with Earth observation. This is the acronym. And let me share the presentation first of all. I hope you can see it in presentation mode. So can you see it?
Sorry, it's not yet in presentation mode. Or at least I don't see it in presentation mode.
I'm trying to make it in presentation mode. Let me see. It's strange because it's.
If not, we can go ahead like this, and later on when.
Okay. Okay. So let me introduce the. Otherwise, we lose too much time. So this is the first of a series of webinars on this topic, using Earth observation data for producing official agricultural statistics. In this presentation there will be two sessions. The first one I will provide a brief introduction, and then my colleague Lorenzo de Simone will get more to the detail and the technical details of the tools and methods that we are using with this project. So I will give, first of all, a brief outline of the scope of the project, the main activities and data that we produce, the list of webinars that we are going to organize in the next few weeks, and then the overall objective that is of standardization of methods and tools, both within FAO and at country level, and also among UN agencies, which is one of the key problems that we face today, the fact that there are so many different methods and tools using Earth observation, and this creates a lot of confusion, especially different results for the users. So let me first start with the scope of EOSTAT. First of all, it was launched by our office in 2019, just before the COVID pandemic struck. The main objective is to build capacity in countries in producing crop statistics using Earth observation, in line with the statistics modernization strategy of FAO and the modernization of national statistical system, which is promoted by the Statistical Commission. Other relevant important objectives are increasing the quality of national statistics in terms of accuracy, timeliness, the level of disaggregation of data, filling the gaps in FAO databases in terms of, for example, agricultural or crop production, promoting innovation through methodological development and adoption of new technologies, and, as I said, supporting the standardization of observation methods and tools for the production of land cover statistics in countries and within FAO. Currently, the project is implemented in 12 countries, and we have already results for many of them. And we hope to expand this to 18 countries during the course of 2018. So what are the main activities and data that we have produced for example, for the Hand-in-Hand initiative, which is one of the flagship initiatives in FAO, which has developed a geospatial platform that is disseminated widely to all countries. So, first of all, we want to produce crop acreage statistics, crop yield statistics, and land cover statistics. Then the idea is also to provide guidelines on how optimize survey design, because we are using in combination field surveys and Earth observation to obtain this crop acreage, yield, and land cover statistics. And this is done also in collaboration with another capacity building initiative of FAO that is called the 50 by 2030 initiative, that aims to produce better quality agricultural data in 50 countries by 2030. Methodology development is one of the key output of this tool, and one of the key features of this project, which tries to obtain these results using less data of what is normally used. Also, because survey data are quite expensive and difficult to collect, and so we also try to reuse in situ data for other areas or other countries. We also developed some tools for the automatic crop classification of data, which is called EOSTAT Crop Mapper. And as I said, this is used to support the standardization of Earth observation methods at FAO, across UN agencies, and across countries. This is done, I mean, of course, the idea is that we develop these methods and tools, but then we hand over these tools and knowledge to countries so that countries are then able to produce data by themselves. And this is done through on-site training, webinars, and seminars. And this is one example of this kind. The hand-in-hand initiative I mentioned before, this is an example of the data that we have provided to this. We have provided up to now 64 national maps developed since 2020. And these are accessible through the hand-in-hand geospatial platform of FAO. So you are most welcome to open the platform and access the data that we have provided there. So the webinar structure, as you can see, we will have 6 sessions. This is the first one. And this is the more general, that introduce main concept and definitions. Then we will focus on specific topics of this project. So first of all, on crop yield mapping and yield statistics, on crop acreage statistics, and then on the survey design and how to improve the survey design in order to collect in situ data that can be combined and integrated with the Earth observation. Then standardized land cover classification for land cover statistics, and the presentation of the tool that we have developed for the automatic classification of land cover statistics, and then crop field boundaries mapping using machine learning and very high resolution data. This webinar will run from March to May 2023 to give you the opportunity to look at the material and maybe study the material, and also come back to us with questions if there are things that you have not been able to understand during the previous webinar. So I mentioned that the standardization, which is one of the key objectives of this project. We have developed a new governance within FAO that involves not only data, not only statistics, but also data, and tries to develop a quality assurance framework that covers not only statistics, but also Earth observation and big data, together with a set of standards to be implemented by FAO and by countries. And we think that by developing this quality assurance framework and some standards, we will then be able to provide a quality assessment of the geospatial products and to see if they are fitness for use for the production of official statistics. Some of the key standards that will have to accompany the quality assurance framework are the revision of the land cover land use international classification, the definition of the minimum requirements for the number of land cover classes and in situ data, the minimum threshold for class accuracy classification and its stability over time, which allows to also produce statistics on land cover change, for example. The production of a standardized workflow for image pre-processing, which is fundamental to obtain good quality images and be able to interpret them correctly. And then a standardized template for metadata documentation, provide all the documents necessary for user to use the tools and the methods that we have developed. As I said, FAO has developed a new governance that includes both data and statistics. This is chaired by the chief economist at FAO and includes all the senior manager, both producer and user of data. The main objective is to ensure greater coherence and enhance managerial support to data harmonization and data innovation. So this data governance group is data coordination group is supported by a technical group which prepares, which is formed by senior technical staff from all units producing data statistics in FAO, and supports the work of the senior manager producing standards that then will be approved by the senior manager. At the global level, we have two governance mechanisms. One is the UNGGIM that was established by ECOSOC as the apex intergovernmental mechanism for making joint decisions and setting direction and standards with regard to the production, availability, and use of geospatial information. And the two of the key products that have been produced are the Integrated Geospatial Information Framework and the Global Statistical Spatial Framework that have been approved, as I said, by the UNGGIM. The second body is the UN Statistical Commission that recently has changed it and expanded its terms of reference to include also data and not only statistics. And data related system. And ECOSOC has adopted this revised terms of reference of mission. So the Statistical Commission has become also a primary standard setter in global standard setter in the area of data and geospatial data. And the UN Statistical Commission has adopted the SD Geospatial Roadmap recently. I just mentioned one last thing, and this is a committee of experts that has been developed and is working under the oversight of the UN Statistical Commission. And this committee of experts that deals with big data and data science for official statistics has established a specific task team on the use of observation for agricultural statistics. Co-chairs of this group are FAO, the World Bank, and the INEGI, that's the Statistical Office of Mexico. And so far, this group has worked on the development of methods and standards, on increasing data sharing through the global platform, for example, that global data platform, where data and tools of spatial data are shared and available to all countries, and through organizing training activities in collaboration with UNITAR and also in collaboration with the other UN agencies. I stop here, and I want to give the floor to Lorenzo, that will give you much more details on the project itself. And I stop the sharing my presentation now. Thank you. I hope.
Thank you, Pietro. We hand over now to Lorenzo. Lorenzo, go ahead.
Good afternoon and good morning. Okay, I'm going to share my screen. Can you confirm that you can see my screen?
It's not in presentation mode.
Okay, but now?
Yes.
Okay, so first of all, thank you for attending this webinar. As Pietro explained, this is the first of a series. In this webinar, we're going to explore the main areas of work of EOSTAT project. We're going to delve into technical details, but not too much, because then we're going to have separate sessions for the specific aspects, where I invite you to join between today and May. Some of you may have already attended yesterday's FAO's presentation for the UN strategy, so this presentation might be redundant for you. So today I'd like to talk about the aspects of the EOSTAT project. As Pietro introduced, the project is really focusing on the use of Earth observation data for the production of official statistics, with a specific focus on crop statistics, acreage, yield, and land cover statistics. So the presentation is articulated over a few key points. First of all, just a brief reminder of the relevance of Earth observation data, land cover, land use data. So Earth observation data and geospatial information in general have been early recognized as instrumental to the modernization of national statistics offices and in support of the operational monitoring of SDGs by the UN General Assembly and by the main Earth observation coordination bodies such as the GEO, the UN GGIM. Earth observation data in general can be used as complementary or as alternative data source to produce a variety of statistics, being these agricultural statistics, environmental statistics, and other socioeconomic statistics. And with a view on official agricultural statistics, in particular crop statistics, Earth observation data come with some intrinsic characteristics that make them useful, such as the large geographic scope, the high spatial resolution, which allows for disaggregation of data, high temporal resolution, which allows for the frequent update of baselines, and nowadays high resolution data comes for free, and in any case the costs for commercial products are progressively lower and lower, so we can have access to commercial products at low cost. Furthermore, the UN GGIM has recognized land cover and land use data as fundamental geospatial data themes for the achieving of SDG targets, and so land cover and land use is among those layers. As we know, land cover informs us on the coverage of Earth's surface, and so it allows us to have an understanding of spatial patterns of biodiversity. We can analyze the effect of climate change, so we can develop management policies based on that. Whereas the land use information allows us to have an understanding of what is the anthropic activity on the land, and especially so have information regarding changes in natural resources, agriculture, conservation, urban development, and of course this has a link to food security. Furthermore, land cover data, land use data may be used for the monitoring and the measuring of specific indicators under specific SDGs, as we will see in a moment. So land cover change, for instance, they can help to inform, to distinguish urban-rural areas in for SDG 1 and SDG 4, distinguish freshwater areas for SDG 6, SDG 9, provide detail within the urban areas for SDG 11, distinguish catchment areas, marine and coastal areas under SDG 14, distinguish forest area, degraded land, and mountain areas within SDG 15. Whereas land use data can help to distinguish agricultural areas under SDG 2, distinguish marine and coastal protected areas under SDG 14, and distinguish forestry area under SDG 15. I will leave aside the land ownership data because we are not concerned with that in this presentation. Regarding land cover data and specifically land cover maps, so the capacity of a country to produce national land cover maps in a standardized way over time is really essential for the production of land cover baseline and for systematically updating this from the maps, as this then will allow in turn for the production of land cover statistics and land cover change statistics and for SDG reporting. This is just an example from a project implemented in Lesotho, where the land cover data is updated using a standardized approach on an annual basis, so that then for every baseline we know that the distribution of the land cover classes, but we can also analyze how those classes are changing in time, so the trends. What is the land cover change between a start within a window of time, but also in this case we have an example of the reporting of SDG 15.4.2, so the mountain green cover index, based on the national land cover data. Another example is the crop maps. So crop maps really inform us on how the agricultural land is being used, and specifically which type of crops are being cropped, and also to distinguish cropped area from non-cropped areas. And of course, there are many applications of crop type maps according to their characteristics. They could be used for early estimates of crop statistics, to disaggregate the crop statistics at sub-national level down to the field level, They can be used in conjunction with modeling for crop yield forecasting. They can be used for early warning purposes, disaster impact assessment, market analysis. This is an example. This map here is an example of a national crop type map. It was produced in Senegal for using the as training data, the agricultural census data. It represents 23 crops, so the major crops and the minor crops. And from the map, it is possible to apply pixel count methods and then to calculate the acreage of cropland and non-cropland and the acreage for each major crop, and then to aggregate that at district level, for instance. So Earth observation data is very promising. However, it's still quite difficult to use it. More in general, the problem that we have framed and we want to solve using the Earth EOSTAT project is that collecting and predicating real-time crop location and yield is difficult and expensive. So the objective is that to provide support to countries to build a technical capacity so that they can consistently collect agricultural statistics through integrated Earth observation data, physical model, and ground truth data collection. And our approach is that to provide this through tools that are available for free publicly, and that they are developed and finely tuned within in-country pilots. So in collaboration with the national stakeholders, who are usually the national statistics offices, but they can also be Ministry of Agriculture, depending on the country. So there are a series of challenges that still make Earth observation data not really an operational tool in countries. And we've grouped them under the area of crop type and crop, so crop acreage and crop yield. The most limiting factor for crop type mapping in the use of Earth observation is the lack of the ground truth data. So the data that is required for the training and the validation of the products, the training of the algorithms. So this is an example of the issue that are usually found. So first of all, it's rare to find this data because it's expensive to collect this data. But when the data is collected, and it is georeferenced, most importantly, when the data is georeferenced, there might be problems with the quality. So for instance, we may have GPS traces which don't make polygons, so they're not closed polygons. This is the case, for instance, of this image here. Or in other cases, we can have GPS single points which are collected on the border of a parcel or at the crossroad between more parcels. Furthermore, we can have GPS coordinates gathered at the location of the household. And all of this makes it very difficult to combine then in situ data, ground truth data with Earth observation data. And then as a result, it takes a lot of time to clean this data, to make sense of it, to transform it, let's say, to a suitable data set for the use of Earth observation. But beyond this, usually another issue with in situ data that can be found when it is georeferenced is that the distribution of the samples per class, per crop type is really biased in the sense that we have an overrepresentation of the major crops and a minor underrepresentation of minor crops, which then turns into a problem of contamination when we produce the map. So we have a low accuracy essentially. Another limiting factor is really the high dependency of the supervised classification methods on a high number of in situ data sets. So there have been some recommendations already made a few years ago by the GECAM, where they advised to use one observation every 5 square kilometers to make a crop mask, and have one observation every each square kilometer for an annual cropland, which can be reduced to one observation every 10 square kilometers for very simple agricultural landscape. But of course, for a large country where we have many agroecological zones and different crops, so those numbers add to thousands, and that's quite demanding to gather this data. And the other problem is that also once we have a data set, it's difficult to reuse it within a different epoch or in a different area. So there have been some experiments carried out by different researchers I'm referring here to an example produced by Sherry Wang et al. So they compared the performance of a random forest and also in the unsupervised Gaussian mixture model that was trained in an area, and then it was applied to a different area on different epochs. And the results, let's say they are decent as long as the two areas are very similar and there is no difference in the growing degree days. But then as the difference start to expand, the accuracy is rapidly decreasing. And of course, they applied this into the in the US Midwest, where we have, let's say, extensive farming. So it's a different thing if we think to apply this instead in small, older farming, so in non-extensive agriculture, and especially in developing countries. So the research is still required in this area. Another issue is, of course, the cloud coverage. So as long as we work with optical data, this is a problem. And when we integrate radar data to compensate, radar brings other type of complexities, for instance, a lower spatial resolution, and it's more complex processing. Regarding the crop forecasting and the mapping of the crop yield, so the issue here is that the traditional methods of yield estimations depend on crop cutting, but they lack a rigorous and standardized protocol for the harmonized data collection. The yield forecast based on the limited number of crop cutting, of course, remains highly uncertain due to the large spatial variability of the samples. And furthermore, crop cuts are often not georeferenced, so it's also difficult to bring them within the geospatial context. And finally, models based on the correlation between regressions between NDVI integrals, for instance, and historical crop yields, usually they have a low predictive power. So this said, the objective of the EOSTAT project is really to address those challenges by using other trusted and already established methods where we have in situ data, but also developing novel approaches to cope with the lack of in situ data. So I will skip this slide because we will go into the details now. Just to mention that the project is implemented in collaboration with international partners. So we're happy to have support from European Space Agency, University of Louvain, the Michigan State University, the UN Big Data Group, the GEO, and the Digital Earth Africa. So going now into one of the activities, so we will go through all of them. So first case is the use of trusted methods in Senegal, Uganda, El Salvador, and Mali, where we could have access to in situ data collected in the country. So essentially, we rely on the Sen2Agri toolbox, which has then evolved to the Sen4Stat toolbox. The Sen2Agri system is an operational standalone processing system which generates agricultural products from Sentinel-2 and Landsat 8 time series along the growing season. It produces 4 types of products, so monthly cloud-free composites, biophysical indicators, crop masks along the season, and the crop type mask. The Sen4Stat is an evolution of Sen2Agri, so it oversees it. It adds the Sentinel-1, so the possibility to use radar data. It also improves the estimation of the area statistics because it weights the area statistics by the accuracy of each class. And finally, it also integrates a crop yield module, so has this new functionality. We have used this, as I said, in 4 countries so far. This is the result for Senegal, for instance. We've run it both in 2018 and 2021. We were able to produce the crop mask and the national crop type mask, crop type map, sorry. You can see the overall accuracy is 96%, so this is quite a good result at the national level. We've seen this map already. What I want to mention is that in the first run, when we developed the map in 2018, relying on the agricultural census data, we had a problem in the quality control because we had to transform a data set which was not optimized for Earth observation data. We had to, let's say, massage it, but then we would lose a lot of data, a lot of useful data. We couldn't make use of it for Earth observation data. Anyway, as a result of the optimization we tried to implement, we managed to have a map which had 78% of overall accuracy. But then as of 2021, we had the possibility to implement an optimized field survey data collection protocol. So along the annual agricultural survey, there was an agreement. So in one specific district, in the Euro district, we implemented an optimized data collection approach. And as a result of this, when we finally could produce the new crop type map, of course, we had a much higher accuracy. And this has led then to this leads to the second activity of the project, which is really the optimization of survey design and field protocol in collaboration, of course, with the NSO, with the country. So I'm sharing just two examples here for Senegal and for Mali. So Senegal, the survey, the agricultural survey is based on a list frame. So as a lessons from the pilot in Euro district, we recommended to include into the agricultural survey, the official agricultural survey, three elements essentially. So georeferencing the parcel boundary with the GPS, so making sure it's a closed polygon. Add an additional GPS point in the middle of the parcel, and also record the location of the crop cuts. And finally, those recommendations have been officially endorsed by the DAPSA, who is responsible for the agricultural census in Senegal. The DAPSA, of course, sits within the Ministry of Agriculture. So it's the Directorate for Agricultural Statistics and Analysis. So these recommendations are now reflected officially for the future agricultural census, agricultural survey. So this is a big result for us. Mali, the survey there is based on area frame, and we are now experimenting. So we are in experimental phase. Of course, there is a long story with Mali because Centuagri was tested there initially already in 2016. So of course, the capacity there has a longer history in geospatial. But our proposal there, what we are experimenting right now, it has been just implemented. So we already have the in situ data. The area of interest was stratified based on crop intensity, deriving this variable from the ESA world cover map, the world cover map. Then a random selection of 300 segments within different zones, and then the manual digitizing of homogeneous crop blocks within the area. So we did the digitizing exercise before going to the field, and then the field unit would use a WebGIS app to walk to the intended segments, and then ODK to collect the field data, so crop type and crop area, and then also another application which would allow them to edit the parcel boundaries in case they found some errors once on the ground. This is still not endorsed as an official practice, but we hope that the positive results of this may lead to a change in that sense. Methodological development, the data frugal classification algorithm. So we implemented this in Afghanistan, Ecuador, and Cameroon. We tried to answer a question here. We said, okay, what can we do when we don't have enough data to run a random forest classifier, which is the de facto the most robust supervised classifier, which is very data hungry, but it has a lot of advantages. So we said, okay, let's experiment something that may work with less data. So in Uzbekistan, we had access to a very good in situ data set, an experimental in situ data set. And what we did, we used this data to train both a dynamic time warping algorithm and a random forest algorithm, providing step-by-step more validation data. So we ran more tests with 5 data points, 10 data points, 15, 20, and so on. And we wanted to see how the two classifiers were performing in terms of overall accuracy. I will just explain how the dynamic time warping works and then to show the result. So essentially, in the dynamic time warping, we first define reference signatures. And this is, of course, a very delicate part because we only have a few points. So we only have, for instance, 5 data points for each crop. So once we establish this signature, we consider that list of signature, I don't know, alpha, cotton, fallow, orchard, and so on. We consider that as a reference library. We've built the signature using the EVI, but of course, we've tested different bands, different combination of bands. So one can experiment more type of curves there. The library can be built in several ways. Then the second part of the dynamic time warping is the building of a dissimilarity matrix. So for every pixel in our study area that we want to classify, we analyzed the dissimilarity between the spectral signature of that pixel with every signature in our library, and then we will match the combination that minimizes this difference, and we will reclassify then that pixel with that specific matching reference crop. So our results, we saw that when we were using from 5 to 10 data points only to train the algorithm, the random forest and the dynamic time warping, so the dynamic time warping would score higher overall accuracy than the random forest. But then when we would increase to 30 data points, 40 data points, then at that point the random forest would perform a higher, statistically significant higher accuracy than the dynamic time warping. And we also tested two types of validation using all of the validation data, or also simulating a reduced validation data set, and the story was confirmed in both cases. So in this context, we believe that random forest is still the option A, but when that option is not applicable, then we can rely on dynamic time warping as an emergency, let's say, solution. The method has been then reflected inside a Google Earth Engine application for the extraction of crop acreage from the Earth observation data. So essentially, the user is building the phenology, the library of spectral signatures directly inside the platform, either uploading in situ data provided by the country, or digitizing on the screen location that he knows. Of course, there is also a function to adjust the in situ data, so to double check the consistency of those signatures, because of course the classification is going to rely on few points, and so those few points have a very big weight, so they need to be very, very accurate. Then the system performs the dissimilarity matrix, and it returns the classified map. This is an example from Afghanistan, and it allows to extract the statistics, the average, but also to have a view on the validation of the map. Further methodological development. So we pushed the system in order to be able to extract crop acreage, but then we said, okay, what about the crop yield? This is very important statistics. So our approach was that of integrating what was already developed into the crop mapping tool that we saw, the crop mapper, with crop yield modeling, and in particular integrating the crop mapper with the physical-based model, which is called the SALUS in this case, developed by Michigan State University, which has quite a long history. The SALUS stands for System Approach to Land Use Sustainability, and basically it models continuous crop, soil, water, and nutrient conditions under different management strategies for multiple years. And the model, of course, needs to be calibrated, and it needs to be fed with data. So part of the data, of course, that the model requires is coming from expert knowledge. So for instance, crop calendars, particular management of crops, knowledge about invasive species. But then the rest of the data that is fed, let's say, to the model is really climate data. So it requires daily precipitation, average temperature, and solar radiation. And we could provide this data using Earth observation data models because there was not enough really weather station for Ecuador. Then we used the national soil map, for the soil data, and then we need to provide, as I anticipated, the management and yield data, because this is required to develop the calibration set of parameters and to evaluate also the model performance. So as the model is performing, we need to have crop yield at specific locations to assess the error. So the crop management parameters include the so the crop parameters, they include the crop location, of course, the crop type, the season, how many seasons do we have? In case of, for instance, in Ecuador, we have 3 seasons, the planting date, the harvesting date, the yield, nitrogen, planting population, and irrigation. And of course, when this information is not available, then we use average condition for that type of crop, for that area, from the literature and in consultation with the ministry. And what the model does is going to simulate all of the plausible yields outcome for major crops for each agroecological zone within the type of management that have been identified as the optimal one, and returns the results in forms of statistics of a map first, so disaggregated crop yield maps, which is then translated into the crop yield statistics. Of course, accompanying each of those activities that we saw, so both the crop acreage and the crop yield, and also the in situ data design, there's always a capacity building component. So there's always a training program, which is distributed both online and in person. And in the case of Ecuador, there was a lot of attention for this. So there was a lot of interest, especially for maize and rice. So we had the Minister of Agriculture in person to attend, Mr. Bernardo Manzano, and he was highlighting a lot the relevance of using this type of approach to have an estimate of the crop yield in advance, so that this information can be used for export and import amounts, for instance. So likewise for the acreage, also the crop yield component then has been translated into an online tool, both for Ecuador and Cameroon. And a new release is going to be announced, where the parameterization of the crop yield can be performed using the graphic user interface, because of course countries, they want to start fresh, so they want to calibrate the model at the beginning, but then the calibration is not really required over a long period, for at least 4 or 5 years, unless there are important changes into the agriculture landscape, introduction of a new crop, for instance. Another activity, it's not really innovative in the sense that field boundary mapping has been already happening in many projects since I think 5-10 years. The thing is that for agricultural statistics, having the field boundaries mapped increases the accuracy, the overall accuracy of both crop acreage and crop yield estimation using Earth observation data, because we go from pixel approach to object approach, object analysis, so we can better deal with the variability within field, variability of the spectral signatures of pixels. So in collaboration with Digital Earth Africa and using in-kind images provided by Planet, 2 pilots have been implemented, one in Rwanda and one in Mozambique. The approach is that of using convolution neural networks and transfer learning model. So the model has been pre-trained using training data from France, training data from India, and we have integrated with more training data from those 2 countries. The approach was developed initially by Sherry Wang, so that we can pre-train a model elsewhere, and then we can use it in Rwanda and Mozambique. So the results are very promising for Rwanda. In fact, we tested in 2 areas, and now we're finalizing the national map of the boundaries, of the crop boundaries. Whereas for Mozambique, we've stopped just at the area of interest level. This is what the workflow looks like from the input and the output. So in the beginning, we have a very high resolution image from Planet. Then we predict the extent probability of the cropped boundaries. And then we map the probability of the boundaries, and finally we segment the image, and then we validate those outputs with the borders of the parcels that have been manually digitized either on screen or in the field. And you can see that we have pretty much higher F1 score, but also the IOU is 0.42, so that's quite good. Finally, the artificial updating of in situ data, the case of Lesotho. So in this context, we had this question. We were thinking, okay, if I manage to have a good training data set, in situ data set, or a good baseline, a reliable map produced in one epoch, for land cover, of course, in this case, and I want to reproduce that map in another year because I want to calculate the land cover statistics, how they changed in time, the trends, and so on. Is there a way for me to reuse that data set? Now, the risk of using that data set as it is in a different year is that we may have a change. We might have a change in the meanwhile on the ground, and so that data set is obsolete. And so it will introduce confusion in our classifier, and it will also omit in the validation data the areas that have changed. So we might not, we might miss to detect commission errors. So in this context, we've used a methodology that is based on the analysis of the strata, so of each land cover class, the analysis of the dominant feature for classifying land cover, which is the NDVI, the geomedian NDVI for the period of the peak vegetation, being calculated within the strata, but obtained from the time series satellite images of the reporting year, so the year for which we want to predict the land cover. So we started from an initial map. We extracted the land cover class. For instance, in this case, we have an example which is the mine site. So in this case, we only see one mines, but the analysis is done for all the mines together. So what we do within the mines, we then overlay the boundary of the mine on the NDVI composite. It's a bimonthly composite, November, December, because in South Africa, that's the peak of the vegetation. And then we run a k-means on the NDVI, and we request 15 to 30 numbers of clusters. So we admit a lot of clusters inside the k-means. As a result, pixels that have similar NDVI are going to cluster together. And we first inspect the distribution of those clusters. And as we can see, we have a major cluster, which is the one that you can see here, the tallest one, so the cluster that has the highest number of pixels, and it's towards the left end of the NDVI scale. So this is telling us that the majority of pixels in that cluster have a low NDVI, and probably that's the dominant cluster. That means that those pixels are still a mine site in the target here. Then we have instead other minor clusters, which we can see both in the chart here, but you can see also here in the map in the blue color and red color. So inspecting those, we realize that the blue areas here are water, the red color here are trees. And statistically speaking, they belong to very small clusters. So we consider them areas where we had a change, or at least now the NDVI has a different value there, statistically different and separable from the major cluster. So what we do, we delete all of those pixels from our pool. So we reduce our mine area to a smaller area that we feel where it's still consistent with the class, with the reference class. And then from this pool of pixels, we randomly select pixels for the training and the validation to calculate the land cover statistics for the reference year. So essentially, we artificially have updated our in situ data. Of course, there is a loss of data in this process. With time, we lose a certain percentage of data, more or less 10% of the pixels are lost every 5 years. That's what we estimated. So when we can't go back to the field to gather new in situ data, we use this solution to artificially update the data, and this allows, of course, to produce the land cover maps regularly on a year basis, but also to validate the products on a yearly basis, and so allow for a consistent mapping over time. During COVID, for instance, we learned that there can be issues to go to the field. There could be other type of issues, conflicts, but also financial constraints. So having a solution for those years where there is no possibility to implement a field survey can be useful. Okay. So I think I still have 5 minutes time. Yes. So I'd just like to elaborate on the use of Earth observation data for the standardization of the SDG 15.4.2, so the methodology. As Pietro anticipated, there is now an initiative to standardize the high heterogeneity, of methods that are used, so that outputs from the use of Earth observation data can be comparable, the quality can be understood, and they can be used for official statistical reporting. So in the case of the SDG 15.4.2, I just would like to share with you which was the process that was used to successfully develop, let's say, a standard methodology, which is recognized international for the measuring of these indicators. So in particular, in 2020, FAO developed a new methodology based on the analysis of land cover and digital elevation data, and the method was also published. Okay, 2020-2021, this method was used by FAO to calculate the SDG statistics for 15.4.2 in collaboration with countries, and then those estimates were sent to countries for validation process. So there was a positive feedback. There was a high rate of endorsement because it was also easy to understand and to validate those statistics that were produced using the method. And finally, the method then was endorsed by the IAG, SDG, and then by the UN Statistical Commission. So that was the process that we used. Furthermore, now the methodology has been further ameliorated in order to integrate a dimension of land degradation, to change the stratification from elevation to climatic zones. But so this would probably trigger now a new, let's say, a new official endorsement. Actually, it's taking place in July. But that's just to say that it is possible to test a methodology, to show the consistency of this, to evaluate the accuracy, and then to propose that as a standard, in this case to the IAG for SDG. The exercise was quite successfully endorsed by the international geospatial community. FAO received the Geo Sustainable Development Goal Award for this work, together with other UN agency for other topics. So that was quite a success story. The maps stemming from the EOSTAT projects are accessible through the end-in-end initial geospatial platform. So altogether, 64 national maps have been developed since 2020. Actually, I think now we're almost 80 of them. Not all of them are already accessible, so some of them are already accessible. The others are being published as we speak. But from there you can access them, or if you're interested in obtaining the GeoTIFF, you can just send an email. The country for which the maps have been produced have already been shared on the platform are Afghanistan, Cameroon, Ecuador, El Salvador, Gabon, Guatemala, Mali, Mozambique, Rwanda, Senegal, and Lesotho. Okay, just some examples of maps. So crop yield maps, they come at 10 meters resolution. This is an example of maize for Ecuador. The legend is expressed in megagrams per hectare, and this is the May for the season 1 in 2018. This is maize for season 2. This is rice for season 1, 2018. This is a crop type map for the Guayas district. This is how the statistics come in terms of aggregated at national and at district level. Cameroon the same, but we have more crops there. So we have rice, cassava, maize, and sorghum. They've been modeled from 2012 to 2020. Furthermore, the land cover map exercise, or the production of land cover statistics, developed in Lesotho, now is being tested in Rwanda and Mozambique. So Rwanda has been finalized and Mozambique is still under processing. The production of the geomedian essentially is still ongoing. El Salvador, an ad hoc in situ survey has just been finalized. So this crop type map should be available by the end of March. So by the end of this month. In a nutshell, the advantages of the EOSTAT approach for crop statistics. So Earth observation data have shown to be capable of quantifying areas and type of crops under cultivation at the district, regional, and country level. The novel method is independent of the self-reporting data coming from local authorities and scalable. So it's an additional tool that does not depend from the traditional workflow. So it adds to the toolbox that country have. It can cope with in situ data scarcity. It increases the cost efficiency of field surveys because we increase the overall accuracy in the end and the quality, overall quality. The application of the FAO EOSTAT project, mapper, has shown to be able to reproduce measured yield observation. The system can scale up results to larger areas beyond the small sample of costly data collection. The Earth observation-based results are science-based and demonstrated to capture the complex feedbacks between soil, climate management, and genetics. And finally, the FAOSTAT crop mapper based on Earth observation linked with process-based crop simulation models has the potential to really modernize, we say revolutionize how the crop yield in areas can be estimated in the future by countries. Thank you very much for your attention. I would like to stop here. Thank you.
Thanks so much, Lorenzo, for this great presentation. We will now, of course, go to the Q&A session. Before we start with the Q&A session, let me just reiterate that if you want to take the floor, please raise your hand, and then we will give you the floor later on. We have also received a number of questions in the chat, and I will probably start with those if possible. So Lorenzo, thank you for this, and let me have a look at the meeting chat, which I'm now struggling a little bit with Zoom. Sorry. Okay. Sorry, I'm lost the chat window for whatever reason. Okay, Lorenzo, if you can take maybe if you can have a look at the chat window yourself for the moment and take one of the questions there, and then I hope in the meantime I can find the window again. Thanks.
Alexander.
Yes.
Do you want me to go through the questions directly? Is that the idea?
Yeah. Maybe you can take one. I think okay. I will be able to do my duty as a moderator in a second.
Sure. Okay. So there is the first question I see. Okay, there's one question on mentorship that's not related to this presentation, but the answer is yes. Richard Thompson is asking, could the EOSTAT project provide statistics on the use of plastic in agriculture, mulching films, greenhouse, protective textile? So regarding the first topic, so plastics, mulching films, greenhouse, protecting textiles, yes. because they have a different detectable spectral signatures. Of course, it always needs to be calibrated. It needs to be seen how big are those areas. And but yes, I would say definitely yes. For the drip irrigation, it depends on. I mean, we can see the effect of irrigation for sure. So we usually detect rain-fed crops and irrigated crops. Monitoring knowing if it's drip irrigation or not, this I'm not sure, I have to say. Then there is a second question from Julie Botsas. Are there concerns in classification bias in doing comparative changes and also in coming up with extent errors? Yes, indeed, there is a problem there. There is a concern because we have, first of all, a bias in the classification year per year. So we do have problems of commission and omission errors, and those then they combine when you do the land cover change. One way for us to control this error is to run an analysis over time, and I guess you're referring to the land cover. One way that we are dealing with that. So first of all, when we do the estimate of the area for every year, we include the standard error in the area estimation. So we correct that area extracted from the map, accounting for the standard error. And secondly, we measure the stability of the accuracy of each class within each epoch. So we created an index. So we ensure that that index is low, and so by that we know that the quality of the map is consistent over time, so that changes that we will identify between the maps are due to change on the ground. There is also a third measure that we use in order to ensure the quality and the reliability of the uncover change. So learning from the experience of Pierre Deforny et al., who developed the European Space Agency Climate Change Initiative time series, essentially we analyzed the land cover through a 3 years epoch. Okay, so we classify some, we define some post-processing rules, so that you cannot have a change, so that some changes are forbidden over that 3 years window to ensure consistency. So for instance, if I have cropland in year 1, and then I have rural settlement in the year 2, and then I have again cropland, that's not possible, because usually once you build up, then you cannot convert again to natural vegetation or to cropland. So we have several let's say strategies to ensure the quality. I hope this satisfies your question. The second question, Madhavan Palan, perspective from a computer vision perspective. Okay, every image segmentation algorithm behaves separately. Some transfer learning could be useful. Fun fact, people know. Okay, this is more than a question, it's a comment. Yes, I agree. Please. Alexander?
Yeah, thanks. Yeah, maybe we can come out to Madhavan in a second.
Sure.
refound the chat window. I'm so sorry for that. No, I want, yeah, let me maybe ask first this question by Anthony. So or Anthony, if you would like to come in. There was a question about when using agricultural census data as in situ data, how do you reconcile that a holding may be reporting a list of crops over a long reference period covering multiple seasons? Yeah, so how do you treat with that?
Okay, so there are two aspects of this: the structure of your in situ data, how to optimize that, and then there is a remote sensing part on how to use the remote sensing to detect the crops in the different season. with a focus on the in situ data. So, for instance, if this is a list frame based survey, so we only have the location, the GPS at the location of the farmer, we need to understand what type of setting is there. So are the plots commonly close to the house of the farmer? In many cases, that's the case. In many instances, that's the case. So we need to make a guess there, and we say, okay, so those plots, they relate to this farmer, and this is the information the farmer is giving us. So those are the most common crops. So this way we try to improve the data set, which otherwise could not be compatible with Earth observation because the geolocation is the house of the farmer, so it's not a crop. Based on that data set and based, of course, interaction with the country, then we need to find some geolocation of the crops of which we are certain. So we need to know where is the maize, we need to know where is the sorghum, okay? Because then we need to build our features for the random forest or the dynamic time warping. Once we do this, once we know specific locations where we are certain 100% that that's the crop for that specific year, then we start to investigate the spectral signatures of all of the data we have in correspondence of all of those plots that deliberately we have associated with a farmer because there was no connection. And we know that there is maize, and we know that in the season 2 there is another crop. So we analyze, of course, the data by season. So we have our time series of satellite images. We segment them by the season we are interested in, and we know which crops are cropped for which season. So in this way, we manage this issue. The information regarding how we manage now the historical knowledge of the crops. So that's more difficult. So if the farmer is telling us that, okay, 3 years ago I cropped crop 1, and then 2 years ago crop 2, last year crop 3. This introduces more risk to have errors, because again I'm talking about crop fields which are not univocally connected to the farmer. So there is that guess exercise that we did. So in that case we can have a problem, and that can be complicated. Having Sentinel-2 data at disposal allows us to go back to 2017, so we can model data in the past if we have the in situ data. In other settings, though, let's say in settings where instead the crop field has been georeferenced, and where we know that those locations there have been different crops in different years and different seasons, then we can go back in time with the satellite data, and we can inspect the growing pattern of the vegetation, knowing that that crop is that specific crop. So we can basically we can classify the map accordingly, because we know which type of crop was cropped when and where. So that's, of course, an optimal situation, but I would be very interested in seeing which country has this data already. That would be great. Thank you.
Thanks. Then maybe let me continue with the next question. There's a question from Gerardo Khalil Hernandez. Gerardo, if you want to come in, please go ahead. If not, I can read the question. So excellent presentation. So what actions are the most important to help support countries to collect EO data? And have you had any experience of Sentinel-2 Agri and Sentinel-2 for STAT models in rotating crops? I think the second question is probably related to the previous one. But yeah, so what actions are the most important?
Can you repeat the first part of the question?
Yes, sorry. What actions are the most important to help support countries to collect Earth observation data?
Okay, so collecting Earth observation data, I don't know if this is a matter of wording, but I think it's more using Earth observation data, because we don't collect Earth observation data. You know, they are collected by satellites. We just download them. We access them through platforms such as Sentinel Hub, Google Earth Engine, Digital Earth Africa. So, but I think that was not the question. The question is more how we make use of it, especially in rotating rotating crops and using the Cent2Agri and the Cent4Stat. So the Cent2Agri was designed, was engineered in order to produce seasonal crop type maps. So within the parameterization is very simple. Once you install your Cent2Agri either at local level or in the cloud, all you have to say is which season you work on, season 1, season 2, season 3, identify your area of interest with a shapefile, and give the start and ending dates of your season, and then provide the in situ data. So as long as you have in situ data informing where are the crops being planted or where the crops are growing, you can have also a survey along the season. That is taken care of.
Okay. Then we have, I see the hand of Sajid Kader. I hope I pronounce your name more or less correctly.
No worries.
Please come in.
Yeah, thank you very much. It was a great presentation, so thanks a lot. Sorry, I might have misunderstood at some point, but I just want to basically double check if I understood correctly. You mentioned during your presentation that for mapping the crop type, the model has been trained on data from specific countries and was used to predict or map crop in other country. So was that the assumptions, or you always have to basically have the in-situ data from the countries that you are modeling the output? So if that is the assumptions, has there been any concern about the kind of similarity of the environmental factors or growth rate in different countries?
So thank you very much, Sir Chill. I think there was a misunderstanding, probably from my side. The mapping of boundaries, which is based, of course, on texture analysis using convolutional neural network, that has been implemented in Rwanda and Mozambique using a pre-trained model, pre-trained with data from France and from India. Okay, it's not the crop type, of course. So it's not related to phenology. It's a texture analysis, essentially. Instead, now, as you mentioned, I think as you asked the question about the concern of different conditions and whether for the crop type, so the crop classification, I think it's interesting, to elaborate on this, even though we've clarified the misunderstanding. So indeed, crops, good practices for the crop classification would be to stratify our approach by agroecological zone, because we can rely on the fact that within the agroecological zone there are more or less similar conditions, and hence you would have, let's say, a better performance of your model if it's optimized, if it's calibrated at agroecological zone level. In fact, into the recommendations of both GECAM but also Cent2Agri, UC Louvain, there is always a recommendation of a certain number of samples per crop per agroecological zone. I hope this replies to your question. Thanks.
Awesome. Thank you very much.
Thanks. Then there were a couple of questions about whether the slides and the recording will be made available. Yes, they will be. We have posted in the chat both the links to the event website, where also information about the upcoming series or the following webinars are being posted. And also we have posted a link to the global network where also the recording and the slides will be posted. Then there were some questions. Sorry. There was a question whether this would be whether this topic will be part of the SDG summit, and I think of the SDG indicator framework. Maybe you can say a little bit about that, how this relates to the SDG indicator. I think you have touched, I mean, I'm sure you have touched upon this, but maybe you can repeat this point. Thanks.
So in relation to how this is connected to the SDG reporting framework and then related initiatives. Of course, geospatial data, and in our context, crop type maps, crop land cover maps, they are functional to measuring specific indicators or part of those indicators, so sub-indicators under the SDG framework. So for instance, using land cover and elevation and now climatic zones allows for measuring 15.4.2, totally relying just on Earth observation data. And of course, you can use global data set, but you can also use national data set, which usually come at a higher resolution and more accuracy. There are other cases instead where you have indicators which include both environmental data or, let's say, land use data that has a geographic footprint, but also with socioeconomic data which does not, you can't map it. For instance, labor cost. Labor cost is a variable we cannot map, but in that indicator you have more components. So thinking, for instance, agriculture, sustainable agriculture 2.41, the original definition when before the proxy was developed. In that context, you had that denominator, you had the agricultural land, and that's where geospatial can have can provide that information. And on the denominator, then you had various criteria of sustainability. Some of these were socioeconomics, but some others instead were related to the productivity, to the fertility of the soil, the salinization of the soil, loss of fertility of the soil erosion. So clearly geospatial data can provide an input into that. So also for the measuring of your agricultural basin and to detect the irrigated crops under the SDG indicators 641 and 642. I think also there the crop type maps they're quite relevant for that. But there is a slide inside the presentation where for each SDG we have mapped the relevance of land use data and land cover data.
Thanks so much. We are slowly approaching, I mean, we still have a couple of minutes, but maybe we can put up again this slide with the upcoming webinars, Lorenzo. So because this is, if you have it at hand.
Just a second, I want to find it, just a second.
Yes, and this is also again an information then for everyone. So please have a look again at the event website and also on the global network, where you will find information about the upcoming.
Can you see it?
Yes. Can you scroll down a little bit? Yes.
So if I may just suggest, so the session 2 and session 3 will be focusing on the yield mapping and the acreage mapping. So if you are curious about knowing the mechanics of the physical base model, how to calibrate it, I think this is the session for you. We will have Professor Bruno Basso, who's globally recognized as one of the most advanced crop modeler. In session 3, we have instead the crop type mapping, hence the acreage, and our guest will be Sophie Bontemps. She has more than 15, 20, maybe 20 years of experience in developing crop type maps. She's been the one, together with Pierre Deforny, in developing the theory behind Cent2Agri and Cent4Stat. On session 4, we will have the improvement of the survey design, using also Earth observation data to improve our stratification. So it's two ways, using Earth observation data to improve the survey design, but also having a survey design that then can be used to classify satellite images. And we will have again Sophie. She will share the experience also in Senegal, in Mali. I think it's going to be very, very interesting. So it's both the survey design, but also the protocol for the data collection in the field. On session 5, we will talk about the standardization of the production of the land cover maps for the extraction of the land cover statistics. We will invite William Ouellet, who is a scientist who has been helping us in the project in Lesotho, and now he opened his own company, which is called SoilWatch. And finally, on session 6, we will have both Sherry Wang from well, she will be she's now in Stanford, but by then she will be moved to MIT. And we will have also a representative from Digital Earth Africa, probably the chief scientist, Lisa Rebello. And we will talk about the project of the field boundary. And so if you're curious about pre-training an algorithm in one area of the world and then applying it in a different area, I think that's the place you want to be. And Sherry Wang again is, and also Lisa, they're very, very competent scientists. Thank you.
Thanks so much, Lorenzo. And Sophie has also shared again in the meeting chat the website. So the basically the link to this page where more information about how to connect for each session will be shared. So please revisit this. And I think I don't see any additional questions right now in the meeting chat. This is maybe just so please join the upcoming webinars. You will be able to ask more questions, Lorenzo more questions, and also the other speakers. And if you wish, you can also reach out to Lorenzo via the global network and ask questions there. We will post the recording and the slides later on there and on the event website. So I think with this, we can probably close. Lorenzo, you want to say some final words?
Well, I wish to thank you, Alexander and Sophie, for the organization, and thank all the participants for your time and for the interesting questions. I hope that we can share more in the future, and this is really a two-way sharing. So we're all here to learn, and I would love, if with your questions you also share your use cases and see, if we can grow collaboration and help each other in the many challenges that are found in the use of Earth observation for official statistics. Thank you so much.
Thank you. And maybe one last one last favor to ask to everyone. Can you please maybe turn on your camera, unmute yourselves now? You are all allowed to unmute yourselves, and give Lorenzo and Pietro a big round of applause. That would be really amazing. So please unmute, put your camera on, and join me. Thank you.
Thank you.
Lorenzo, thank you.
Oh.
Thank you.
Great.
Okay.
Thank you.
Thanks,
you.
Thanks everyone for joining. Join us again next time for our next Global Network webinar or our next FAO webinar. Thanks and have a good rest of your day. Bye-bye.
Bye.
Forward to the video. Thank you.